This is Anita Wood, and welcome to this topic snippet video on computer components and operations. Now, I'm confident that because you're enrolled in a course leading you towards the programming profession, some of what I'm covering you may already know. However, what I need to do is make sure that we are all using the same terminology and definitions. Being able to correctly speak in computerese will make or break your career. So I'm not trying to talk down to you. I respect your previous knowledge, but I must do my due diligence and make sure that we are all, as they say, singing from the same songbook. So let's get started with computer components and operations. Sit back while we watch this video clip, and I pass my teaching role to others.
My name is Mei Li Ku, and I'm a designer and an inventor. So some of the things I've designed have been at Apple, and now I design products for kids to use so that they can have an easier time in school. My other jobs include DJing and dancing. Computers are everywhere. They're in people's pockets, they're in people's cars, people have them on their wrists, they might be in your backpack right now. But what makes a computer a computer?
What does make a computer anyway?
And how does it even work?
Hi, I'm Nat. I was one of the original designers of the Xbox. I've been working with computers since I was maybe 7 years old, and now I work on virtual reality. As humans, we've always built tools to help us solve problems. Tools like a wheelbarrow, a hammer, or a printing press, or a tractor trailer. All of these inventions helped us with manual work. Over time, people began to wonder if a machine could be designed and built to help us with the thinking work we do, like solving equations or tracking the stars in the sky. Rather than moving or manipulating physical things like dirt and stone, these machines would need to be designed to manipulate information.
As the pioneers of computer science explored how to design a thinking machine, they realized that it had to perform 4 different tasks. It would need to take input, store information, process it, and then output the results. Now, this might sound simple, but these 4 things are common to all computers. And that's what makes a computer a computer.
The earliest computers were made out of wood and metal, with mechanical levers and gears. By the 20th century, though, computers started using electrical components. These early computers were really large and really slow. A computer the size of a room might take hours just to do a basic math problem.
These machines are things of gleaming, vari-colored metal and numerous flashing lights.
Computers started out as basic calculators, which was already really awesome at the time, and they were only manipulating numbers back then. But now we can use them to talk to each other, we can use them to play games, control robots, and do any crazy thing that you could probably imagine.
Modern computers look nothing like those clunky old machines, but they still do these same 4 things.
First, we're going to talk about input. This is my favorite because what input is the stuff that the world does or that you do that makes the computer do stuff. You can tell a computer what to do with the keyboard, you can tell them what to do with the mouse, the microphone, the camera, and now if you're wearing a computer on your wrist, it might listen to your heartbeat, or in your car, it might be listening to what the car is doing, and a touch screen can actually sense your finger and it takes that as input on what it's doing.
All these different inputs give a computer information which is then stored in memory. A computer's processor takes information from memory, it manipulates it or changes it using an algorithm, which is just a series of commands, and then it sends the processed information back to be stored in memory again. This continues until the processed information is ready to be output. How a computer outputs information depends on what the computer is designed to do. A computer display can show text, photos, videos, or interactive games, even virtual reality. The output of a computer may even include signals to control a robot. And when computers connect over the internet, the output from one computer becomes the input to another, and vice versa.
The computers we use today look really different from the earliest thinking machines. And who knows what the computers of tomorrow will be like. My hope is that you get to help decide what you want the computers of tomorrow to look like. But across all computers, regardless of the different types of technology they use, they're always doing the same 4 things. They take in information, they store it as data, they process it, and then they output the results.
Just to reiterate what was presented in the video, a computer is an electronic data processing device which accepts data input, stores data input and processes the data input, generates the output in a required format. Now this graphic shows the basic logical structure of all types of computers. While we're talking about input being processed to give output, we need an important terminology lesson. Computer scientists make a point to distinguish between the terms data and information. Data is what is inputted to be processed, and the information is the processed data that is presented in an understandable format. Data can be defined as a representation of facts, concepts, or instructions that are presented in a manner that is suitable for communication, interpretation, or processing by humans or other electronic machines. Data is represented with the help of digital or analog signals, characters like the alphabet A through Z, 0 through 9, or special characters. Now, information, on the other hand, is organized and formatted data, which has some meaningful value for the receiver. It is the processed data on which decisions and actions are based. For decisions to be meaningful, the information must have the following characteristics. It has to be timely. Information should be available whenever it's required. It has to be accurate. Not much needs to be said there, but it has to also be complete. Information must present the entire results from the processing, not just a small part of it. Here is a more detailed table that turns the logical operations of the basic computer into specific operations for converting raw input or our data into information useful to its users. First, you take data as input. Then you store the data or in the instructions in a memory, and you use them when they're required. The computer then processes the data and converts it into useful information. It generates the output, and the computer controls all these steps that are up above, all those 4 steps. So here's a graphical representation of the various computer components that provide the operations we just talked about. We're going to walk through this graphic in detail. First are the input devices. These are devices which are used to enter the data into the computer. So really what it is a link between the user and the computer. Input devices, they must translate that data into a form understandable by the computer. For instance, when I press a key on the keyboard converts the pressure on the key into a signal the computer will understand. The keyboard must make a distinction between me pressing the G key or the H key. Think about your day yesterday. What types of input devices did you interact with as you went through your normal activities? I want you to go beyond the typical keyboard and mouse. Here's some common examples that I came up with. You have a touch screen on your phone, your camera, whether it's on the phone or not, the voice recorder, trackball, graphics tablet, the thermostat in my house, video game controller, magnetic tape, a LiDAR, and LiDAR, that's pretty cool. It's a laser that's going to detect the range of objects, okay? How far away something is. Biometric devices like the fingerprint scanner, barcode readers, and for those in the room with a distinct history with the computers like me, punch cards. Now, I do want to share with you one that I was surprised to find the other day. I had an opportunity to take a ride on a cabin cruiser, and the captain used a joystick to steer the boat. That was a first for me. Now, to the next computer component, the central processing unit, or the CPU. The CPU is considered the brains of the computer. It's responsible for storing and processing the input, and also retrieving and presenting the output. Now, the CPU itself has the following three subcomponents: a memory unit, which stores data, intermediate results, and instructions, which is the program; a control unit, which controls the operations of all parts of the computer; and an arithmetic and logic unit. These perform all types of data processing operations. So let's look at those subcomponents in more detail. The memory unit stores instructions, data, and intermediate results. This unit supplies information to the other units of the computer when it's needed. All inputs and outputs are transmitted through main memory. It's also known as internal storage unit, or main memory, or primary storage, or random access memory, or RAM. Now, memory size affects the speed and the power and the capability of the entire computer. Memory has a characteristic that's very important called being volatile. Volatile means the information in memory will only be available when there's power to the memory unit. This means when you experience that infamous blue screen of death, or a power crash, or the power is removed from the computer at all, the memory loses power. Any information that was in memory is lost to the degree that it cannot be recovered. Functions of the memory unit are: it stores all the data and the instructions required for processing. It stores intermediate results in processing. It stores final results of processing before these results are released to the output device. Let's step away from the computer components just a minute for a discussion on another important concept regarding memory specifically. Now, memory is really large and it's capable of storing gigabytes worth of data. To store and retrieve data from memory, the computer locates the specific location in memory using addresses. These addresses are like the ones we use within our neighborhood. Now, the numbering system that's used to create these addresses is called hexadecimal system. The hexadecimal is a numbering system that's used for representing memory addresses because it can represent very large numbers with few digits. We're not going to really go into too much further discussion about this. The textbook does have an appendix explaining the hexadecimal numbering system. And FYI, you're really going to need to learn this and put it into your programming tool set, but just not for this course. So back to the topic at hand. The second subcomponent of the CPU, the control unit, controls the operations of all parts of the computer, but it does not carry out any actual data processing operations. So it doesn't process or store data. It just controls the flow of the data. Functions of this subunit are: it's responsible for controlling the transfer of data and instructions among the other units of a computer. It manages or coordinates all the units of the computer. It obtains the instructions from the memory, interprets them, and directs the appropriate unit to complete the appropriate operation. It communicates with information in I/O, input-output devices, for the transfer of the data or the results from storage. The final subcomponent of the CPU is the arithmetic and logic unit. It accomplishes two very distinct operations. The arithmetic operations, these are the ones we learned in elementary school: addition, subtraction, multiplication, division. The second operations are logical. Now, logical operations include comparing, selecting, matching, and merging of data. We're going to go a little bit further in a discussion about logical operations very soon in the course. So, where does the data get stored with persistence? Now, persistence is a term used to mean remaining available even after the computer is turned off. Another term for this is non-volatile. As computer users, we are quite familiar with the non-volatile storage. Prior to the prevalence of cloud storage, I was constantly investing in external hard drives to store or back up my data. Where is the hard drive represented in this chart? Using my understanding, your understanding of the CPU, it's best represented here off the control unit of the CPU. Finally, the computer's output is why we use a computer. It's to see the results of the processing. When I say see, I mean have the processing results presented in a form that is understandable to us. It is another link between the user and the computer. Now let's see if we can associate those operations that we initially talked about with the various components I just detailed. So I'm going to demonstrate how this little game works. The operation take input, or number 1 in the right chart, is associated with the component input unit on the left. Now, where would you put number 2, or control the workflow? There you go, in the control unit. Where does store data, or number 3, go? Actually, because I introduced the hard drive, it's in memory and the hard drive. Where does processing data, or number 4, go? There you go, down in the arithmetic or logic unit. And obviously it's easy to see where output belongs. I'll give you that one. Okay, so here is the completed exercise. Now we have a pretty good idea of the operations of the computers and the associated components inside the computer. Let's break down the components further by introducing a different way to categorize how computers operate. Specifically, we need to define what is accomplished using computer hardware and what is accomplished in the software of the computer. So terminology time. When we're using these two categories, the physical equipment or devices associated with the computer is hardware, and the software is what tells the hardware what to do. Starting with software. There are two subcategories used to describe software. The first is system software, which manages your computer, such as the operating systems. Now, we're familiar with operating systems. Operating systems are what could be referred to as the foundational software everything on the computer runs on. You have to have the operating system in place before you can install or run any other software. Software, like the second subcategory, is called application software. A simplistic definition for application software is we use it to accomplish tasks. You grew up with computers and use them almost every day. Remember, application software helps us accomplish tasks. Spend a minute and see if you can give a few examples of particular application softwares that you use frequently. I encourage you to turn off the video and give this a try before you see my examples. Here's the examples I came up with. They're not inclusive at all. Every day, new applications are being marketed. But here are the logos for Photoshop, Facebook and its friends, Microsoft Office, Minecraft, Chrome, Netflix, and Zoom. I know this discussion and exercise seems tedious. However, I strongly believe you must have a basic understanding of how the computer works to be a successful programmer. I equate it to being a driver of a car. To drive a car, you must understand the basic components of the car and how they work. For instance, the gas and brake pedals, the steering wheel, the gas gauge, and tank. Without this basic understanding, it'd be really difficult to efficiently and effectively use the car to get from point A to point B, like from getting from your home to Come and Go to stock up on your late night snacks. You do not need to have the same knowledge of the car as your mechanic. Similarly, you do not need to have the same knowledge of the computers as the computer designer. So now we're going to take our journey closer to what we as programmers need to know about programming a computer or designing items for the processing operation of the computer. Programmers write programs that are executed on computers. We learned earlier these computers have a particular way in which you can communicate with them. Let's take a step back away from computers just a second. The first thing you must understand when you're learning to communicate with someone or something is what is the communication language the recipient understands. For instance, when you're going to Spain and wish to communicate with a resident, you must speak Spanish. We want to learn to communicate with a computer. So what language does the computer understand? Computers are electrical by nature, and electricity is based on something being on or off. Computer scientists represent the concept of 1 or 0. 1 equates to on, off equates to 0. So the computer needs to have everything it processes represented as ones and zeros. These ones and zeros are better known as machine language. Thus, machine language is the language understood by a computer. Now, it's very difficult to understand, but it is the only thing that the computer can work with. Early computers were programmed by turning switches on and off. The output was represented by lights, either on or off. We saw these computers in the video we watched at the beginning of class. Over time, computer scientists improved how we talk to computers. They did not change the language of the computer, just added a layer between us and the machine language. This layer is what we'll call programming languages. We're familiar with these terms either through your reading or just general exposure. Programming languages are for humans to read and understand. Over this semester, we're going to be exposed to Java and learn C#. C# is what we will be concentrating on in the CIS 169 component of the class. Using a programming language, programmers code a program. The program they write is also referred to as source code. I'm going to add a term here the book does not introduce, program statement. A program statement refers to a line of code. An example of a line of code could be something like the statement in C# shown here, print hello world. The program or source code must be translated into machine language so the computer can execute the program. This translation is done by a program itself called the compiler. Another translator program is called an interpreter. Whether your program is translated using a compiler or an interpreter is beyond the scope of this course. But this distinction will become important as you progress in your learning. We're only going to speak of them as the same and in general refer to the compiler. So a compiler takes the program code and it converts it into machine language. Sometimes machine language is also called object code. It is the machine language that's executed or run by the computer. Now, the compiler's job is to translate. And as you know, when you're attempting to converse with someone in Spain, you must construct your sentences in Spanish using a particular set of words and rules. If you do not follow these rules, the person you're speaking to will not be able to understand you. This person is not going to find out where the bathroom is unless he uses correct Spanish. The compiler will respond to statements that are incorrectly written by the programmer in a very similar way as the girl responds here. I do not understand. Making these types of mistakes, ones that the compiler cannot understand, are called syntax errors. You must correct these errors before the compiler can complete its translation process to machine language. But syntax errors aren't the only errors that you may have in your code. Sometimes a program is free of syntax errors. The machine code is created and executed, yet the results that you are looking for are not outputted. What's causing the output to be wrong goes to a deeper issue with your program. For a program to work, the programmer must give the instructions or program statements to the computer in a specific sequence called the logic of the computer program. Logic errors or semantic errors include instructions that are out of sequence. They could be missing instructions, or the errors could be because the instructions are not part of the procedure. In other words, you're using an otherwise correct statement that doesn't make sense in the current context. Now, be aware, logical errors are much more difficult to locate than syntax errors. Now that ends this topic snippet video on computer components and operations.